the mean value theorem. Before we state the mean value theorem, we first concentrate on Rolle's theorem. If you have a differentiable function f on a closed interval from a to b, and f of a is equal to f of b, then we can find a c in the inner part of the interval, so between a and b, with the property that the derivative of f at c is equal to 0. This is illustrated by this graph. Here you see the graph from a to b of a function, and f of a is equal to f of b. Then we can find the c in between a and b such that the tangent line to the graph is horizontal. Let us give a proof of this theorem. We consider two cases. The first is that the function f is constant. Then of course the derivative at any c in the interval will be equal to 0. If f is not constant, then as f is differentiable, it is also continuous. And the min-max theorem tells us that there will be a c in the interval where the function attains its maximum or minimum. But then we can find this maximum or minimum at this c and can deduce that the derivative at this c is equal to 0. So in both cases we find that there is a c in the inner part of the interval such that the derivative of f at c equals 0. The mean value theorem is just a generalization of this theorem of Rolle. Now you just take function f to be differentiable again on an interval from a to b, and now we can find a c just between a and b where the derivative of f at c equals fb minus fa divided by b minus a. You can consider this fb minus fa divided by b minus a the average slope of the graph. It is namely the slope of the line that starts in the point a, fa and goes to b, fb. So the mean value theorem says that we can find a c between a and b where the slope to the graph is parallel to the slope of the line through a, fa, b, fb. To prove the mean value theorem, we just use Rolle's theorem. It is a special case, but it is also the key to the proof. Indeed, we can apply Rolle's theorem to a function that we obtain from f. We namely take f of x minus the mean slope times x minus a. So we subtract more or less this line through the points a, fa and b, fb from the function f. This new function takes in a the value f of a. In b it takes the value, just plug b into this formula, f of b minus f of a, and that will be exactly f of a again. So we do have the property that is required for Rolle's theorem. And then it's just an easy consequence that you can do yourself to find out that the mean value theorem is a result of this. What is more important to us right now is that we can apply the mean value theorem. Here is the first application. Of course, we already know that the sine of x is less than x for all x between 0 and 2 pi, but now we are in a position to give a proof. Indeed, for x between 0 and 2 pi, Rolle's theorem says that sine of x minus sine of 0 divided by x minus 0 is equal to the cosine of some c, where since the cosine is the derivative of the sine, and the c is in between 0 and x. But that means that sine of x divided by x is less than 1. And from this we easily deduce that the sine of x is less than x. Another application is the result that the tangent of x is bigger than x if we have x between 0 and pi over 2. And again, we use the same trick. Consider an x between 0 and pi over 2, then the sine of x the tangent of x minus the tangent of 0 divided by x minus 0 is equal to the derivative of the tangent at some point c. And this derivative is equal to 1 plus tangent square of the c, and c is in between 0 and x. Of course, this implies that the tangent of x divided by x is bigger than 1, and hence the tangent of x is bigger than x. Yet another application. If you have a positive x, then 1 divided by x plus 1 is less than ln of x plus 1 minus ln x, and that again is less than 1 over x. Let us give the proof. Suppose you do have a positive x, then ln of x plus 1 minus ln x divided by x plus 1 minus x is equal to the derivative of the ln at some point y between x and x plus 1. As this derivative is 1 over y, we do find that this quotient is in between 1 divided by x plus 1 and 1 divided by x. And we can conclude that 1 over x plus 1 is less than ln of x plus 1 minus ln x, and that again is less than 1 over x.